What lurks at the heart of every galaxy? Something so massive, so powerful, it bends space and time itself into an inescapable abyss. Supermassive black holes, the universe's most enigmatic giants, sit at the center of nearly every galaxy, including our own Milky Way. These cosmic monsters are not just holes in space, they're engines of destruction and creation, devouring stars' entire solar systems while simultaneously shaping the very fabric of the cosmos around them. And yet, despite their terrifying power, they remain some of the greatest unsolved mysteries in all of science. Imagine an object so dense that not even light can escape its grasp. A place where the laws of physics as we know them break down entirely. These are the realms of supermassive black holes, where gravity reigns supreme and reality twists into something beyond human comprehension. But here's the thing, these colossal beasts aren't just lurking out there in the void. They're active, dynamic, and far stranger than we ever imagined. Some spin at nearly the speed of light, flinging jets of superheated gas across thousands of light years. Others collide in cosmic dances that send ripples through space-time itself. And some might even hold the key to understanding the origins of the universe. Today, we're diving deep into 30 of the most mind-bending mysteries surrounding these galactic titans. From the way they form and grow to the bizarre effects they have on their surroundings, we'll explore questions that push the boundaries of our understanding. How do they get so impossibly large? What happens inside their event horizons? And could they, in some way, be gateways to other dimensions? This isn't just a journey through space, it's a voyage to the edge of known science, where every discovery raises even more thrilling questions. So strap in, by the end of this, you'll never look at the night sky the same way again. How can something grow so large that it defies the very laws of physics? Supermassive black holes challenge our understanding in ways few cosmic phenomena can. Take Ton 618, for example, a behemoth weighing in at 66 billion times the mass of our Sun. Its existence alone shatters expectations because, according to the Eddington limit, black holes shouldn't be able to accumulate matter this quickly without radiation pressure blowing away the surrounding gas. Yet here they are, scattered across the universe, laughing in the face of what we thought was possible. One leading theory suggests these giants skip the usual growth spurt entirely. Instead of starting small and gradually feeding, they might have formed through direct collapse, catastrophically dense clouds of primordial gas collapsing straight into black holes with masses thousands of times greater than the Sun from the very beginning. Picture a cosmic shortcut where the rules of star formation never applied. Another wild idea, runaway mergers. In the chaotic early universe, galaxies collided frequently, and their central black holes could have slammed together over and over, piling up mass like a snowball rolling downhill. But the real puzzle isn't just how they got so big, it's how they did it so fast. Some of these monsters were already billions of times the Sun's mass when the universe was less than a tenth of its current age. That's like finding a skyscraper in the middle of the Stone Age. Every discovery pushes us closer to rewriting the textbooks, proving that when it comes to black holes, the universe still has plenty of surprises up its sleeve. The seed problem is one of the most stubborn puzzles in black hole science. How did these cosmic titans get their start in the first place? There are two leading theories, and both come with glaring holes. On one hand, we have the stellar remnant hypothesis, the idea that supermassive black holes grew from smaller ones left behind by the deaths of massive stars. But here's the catch: it would take far too long for these stellar mass black holes to accumulate enough material to reach the sizes we're seeing in the early universe. It's like trying to build a mountain one grain of sand at a time before breakfast. Then there's the more dramatic alternative, primordial seeds. These would have formed directly from collapsing gas clouds in the universe's infancy, bypassing the star stage entirely. Picture vast, dense regions of hydrogen and helium collapsing under their own gravity, skipping straight to black holes with thousands of solar masses. It's an elegant solution, but recent observations from the James Webb Space Telescope have thrown a wrench in the works. JWST has spotted quasars, luminous disks of matter swirling around supermassive black holes, shining brightly when the universe was less than 700 million years old. That's barely enough time for even primordial seeds to balloon to the required sizes. So what's really going on? Some theorists suggest hyper-efficient feeding mechanisms where black holes devoured matter at rates we once thought impossible. Others propose a third path: black hole seeds might have formed from the direct collapse of dark matter, a mysterious substance that makes up most of the universe's mass but doesn't interact with light. Whatever the answer, one thing is clear: the universe seems to have played by a different set of rules in its youth, and we're only just beginning to decode them. What if falling into a black hole didn't mean instant doom? While smaller black holes shred anything that ventures too close with terrifying tidal forces, a process colorfully known as spaghettification, supermassive ones might actually offer a temporary reprieve. Their immense size means their event horizons are far more forgiving. Picture the difference between diving into shallow water versus a deep pool. Near a stellar mass black hole, the gravitational pull is so extreme that the difference in force between your head and feet would stretch you into a noodle before you even crossed the event horizon. But near a supermassive giant like Sagittarius, a star at the Milky Way's heart, the tidal forces are spread out over such vast distances that you could theoretically cross the point of no return intact, at least for a little while. This isn't just speculation. The universe has already given us a test case. In 2014, astronomers watched a mysterious gas cloud named G2 swing perilously close to Sagittarius, a star. Scientists expected it to be torn apart, its material devoured in a spectacular cosmic feast. But G2 surprised everyone. Instead of disintegrating, it stretched like taffy, then kept right on moving. Some researchers now think G2 wasn't just a gas cloud, but a star cloaked in thick gas, its gravity holding it together against the black hole's pull. Others propose even wilder ideas, like hidden magnetic fields or exotic physics shielding it from destruction. Could this mean something or someone could survive a trip near a supermassive black hole? The math suggests that for a brief window, the answer might be yes, but don't pack your bags just yet. While the tidal forces might not shred you instantly, the other hazards, crushing gravity, lethal radiation, time dilation, warping reality itself, would still make it a one-way ticket to oblivion. Yet the mere possibility of survival, however fleeting, rewrites what we thought we knew about these cosmic monsters. It's a reminder that in the universe's most extreme environments, the rules are never quite what they seem. Dark matter may be the universe's best-kept secret, invisible, undetectable, yet making up 85% of all matter in existence, and supermassive black holes might just be the key to unlocking its mysteries. At the heart of galaxies, astronomers have noticed something peculiar. The mass concentrated in galactic cores far exceeds what visible stars and gas can account for. This discrepancy points to an unseen gravitational anchor, and one compelling theory suggests dark matter and supermassive black holes are tangled in an invisible cosmic dance. Some researchers propose these black holes could act as dark matter traps, their immense gravity pulling in the elusive particles like a magnet collecting iron filings. Over eons, dark matter might accumulate around them, effectively creating a hidden halo that explains the missing mass, but the connection could run even deeper. A controversial idea known as the dark matter annihilation hypothesis suggests something extraordinary. When dark matter particles collide near a black hole's event horizon, they could annihilate each other in bursts of energy. Picture two ghosts colliding in the dark, suddenly flashing into light. If true, this process might even explain the bizarre luminosity of some active galactic nuclei. where black holes shine brighter than entire galaxies without enough visible fuel to account for it. Then there's the radical possibility that supermassive black holes didn't just gather dark matter, they were born from it. In the early universe, dense clusters of dark matter might have collapsed directly into black holes, skipping the usual stellar formation process entirely. It's a theory that flips traditional astrophysics on its head, suggesting these cosmic giants could be dark matter made manifest. Yet for all these tantalizing ideas, proof remains elusive. Dark matter refuses to interact with light or ordinary matter, making it notoriously difficult to study. Even the most advanced detectors have come up empty-handed. But supermassive black holes offer a unique laboratory. Their extreme environments might be the only places in the universe where dark matter's secrets are forced into the open. Future telescopes designed to study the regions around these black holes could finally reveal the invisible hand shaping our cosmos. Until then, the connection between dark matter and supermassive black holes remains one of the most thrilling and frustrating enigmas in modern astronomy. What if black holes aren't just cosmic vacuum cleaners? What if they're also cosmic fire hoses? At the edge of theoretical physics lies a mind-bending possibility: the existence of white holes, the explosive opposite of black holes. While a black hole's gravity is so strong that nothing escapes, a white hole would violently repel anything approaching it, spewing out matter and energy like a cosmic geyser. Some scientists speculate these mysterious objects could be lurking on the other side of supermassive black holes, and they might already be sending us signals across the universe. Roger Penrose's conformal cyclic cosmology theory paints a picture where black holes transform into white holes over unimaginable timescales. Imagine a black hole slowly evaporating through Hawking radiation until bang, it rebounds as a white hole, ejecting all the trapped matter and energy back into the universe. This process could take longer than the current age of the cosmos, but some modified theories suggest microscopic white holes might pop into existence far quicker. And here's where it gets wild: certain high-energy cosmic rays and fast radio bursts, those mysterious blips of energy from deep space, could actually be white hole belches from other universes or distant epochs of our own. Gamma-ray observatories have detected explosions that defy conventional explanations. In 2019, the HESS telescopes caught gamma rays with energies that shouldn't exist under standard particle physics, some reaching 100 trillion electron volts. That's like catching a baseball with the energy of a speeding bullet. Even stranger, these gamma rays arrive in patterns that don't match any known astrophysical sources. Could they be fingerprints of white hole activity? The most tantalizing clue comes from fast radio bursts, those millisecond-long radio signals that cross billions of light years. Some repeat in chaotic intervals, while others fire just once and vanish. Traditional explanations point to neutron star collisions or magnetar flares, but the energy signatures don't always add up. White holes could provide an alternative source, their violent births emitting precisely the kind of brief, intense signals we're detecting. Of course, skeptics argue these phenomena have simpler explanations. But in science, it's often the radical ideas that push understanding forward. Whether white holes exist or not, the mere possibility forces us to reconsider how black holes and the universe itself might operate on scales we're only beginning to glimpse. If even a fraction of these observations trace back to white holes, it would rewrite not just astrophysics, but our place in a far stranger cosmos than we ever imagined. Galaxies and their supermassive black holes are supposed to grow together, a cosmic partnership so fundamental that astronomers call it co-evolution, but NGC 1277 didn't get the memo. This ancient, fast-spinning galaxy is missing something crucial at its core, the gravitational monster we'd expect to find lurking there. While most galaxies the size of NGC 1277 host black holes weighing millions or even billions of suns, observations reveal nothing but eerie silence where a supermassive beast should be. It's like finding a sprawling city with no mayor, no government, just empty streets where the seat of power ought to be. So where did its black hole go? One possibility is gravitational recoil, a cosmic slingshot effect so violent it could eject even the mightiest objects. When two supermassive black holes merge during a galaxy collision, the resulting gravitational waves might kick the newborn black hole clear out of the galactic center at speeds over 3,000 miles per second. Picture two spinning tops colliding, except instead of stopping, the combined top goes flying across the room. Simulations show these rogue black holes could travel hundreds of thousands of light years, leaving their home galaxies behind. Yet there's no trace of a runaway black hole near NGC 1277, which leads to another tantalizing theory. What if it's not missing, just hiding? Some supermassive black holes enter dormant phases, starving as they exhaust nearby gas and dust. Without a glowing accretion disk to betray their presence, they become nearly undetectable. Our own Milky Way Sagittarius, a star, is a prime example, quiet today, but evidence suggests it was a ravenous quasar just a few million years ago, the most radical explanation. NGC 1277 might have defied the rules entirely, forming without a central black hole from the start. In the early universe, turbulent gas dynamics or unusual dark matter distributions could have prevented the collapse needed to seed one. If true, this galaxy isn't just an oddity, it's a living relic from an era when the universe played by different rules. Whatever the answer, NGC 1277 forces us to question one of astronomy's foundational beliefs. If galaxies can exist without these cosmic anchors, everything we thought we knew about galactic evolution might need rewriting. The search for more renegade galaxies is already underway because in the cosmos, the exceptions often reveal far more than the rules. Stretching 25,000 light-years above and below the Milky Way's disk, two colossal orbs of gamma-ray energy dominate our galaxy's hidden landscape, the Fermi Bubbles. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these faint but enormous structures glow with the aftermath of some cataclysm that erupted from our galaxy's core long ago. Their sheer scale is staggering. Each bubble could contain the energy of 100,000 supernova, yet their origins remain one of the most heated debates in astrophysics. Did they form from a violent outburst of our supermassive black hole, Sagittarius, a star, or could they be evidence of something even stranger, dark matter annihilating itself in the galactic heart? The leading theory points to a dramatic black hole awakening. Around 6 million years ago, Sagittarius, a star, might have briefly transformed into a miniature quasar, devouring surrounding matter and launching jets of superheated plasma at near light speed. These jets would have punched through the Milky Way's gas, carving out the bubbles we see today. Supporting this idea are the bubble's sharp edges, too crisp for a slow, steady process, and the presence of high-energy particles that match predictions from black hole jet models. It's as if our galaxy's quiet core once hosted a cosmic fireworks show, with Sagittarius, a star, as the pyrotechnician. But there's a twist. The bubble's gamma-ray signature doesn't perfectly align with known black hole activity. Some researchers argue the energy distribution looks more like what you'd expect if dark matter particles were colliding and annihilating each other near the galactic center. In this scenario, the bubbles aren't remnants of a black hole's tantrum, but a shadowy fingerprint of the universe's most elusive substance. If correct, it would be the first indirect evidence of dark matter's interactions on a galactic scale, a discovery that could redefine particle physics. Adding to the intrigue, the bubbles aren't alone. X-ray observations reveal matching structures in the Milky Way's halo, dubbed the eerie bubbles, though these appear older and more diffuse. Are they relics of an earlier outburst or proof of multiple feeding episodes from Sagittarius, a star? Even more puzzling, some galaxies like Messier 87 show similar Fermi-like bubbles, suggesting this phenomenon might be universal, a hidden phase in the life cycle of supermassive black holes. The debate rages on, but one thing is certain: these ghostly structures are rewriting our understanding of galactic ecosystems. Whether fueled by black holes or dark matter, the Fermi Bubbles remind us that even our own backyard holds cosmic mysteries on a scale we're only beginning to fathom. The next generation of telescopes, like the Cherenkov Telescope Array, aims to peer deeper into their high-energy glow, potentially settling the debate once and for all. Until then, they stand as towering monuments to the forces that shape galaxies, visible only in the silent language of gamma rays. The universe was barely taking its first breaths when ULA's J1342+0928 ignited, a brilliant beacon shining across 13 billion years of cosmic history. This ancient quasar, spotted when the universe was just 690 million years old, shouldn't exist. At its heart lies a supermassive black hole weighing in at 800 million times the mass of our Sun, a cosmic heavyweight that somehow packed on billions of solar masses before the universe had even finished its toddler phase. Standard black hole growth models hit a wall here. Even if a black hole started as a massive seed and fed continuously at the maximum possible rate, there simply wasn't enough time for it to reach this staggering size. It's like finding a skyscraper in the middle of a construction site where the foundation was poured just yesterday. The sheer existence of ULA's J1342+0928 forces us to confront an unsettling truth. Either black holes grew faster in the early universe than physics allows, or our understanding of cosmic infancy is fundamentally flawed. One radical solution flips Einstein's playbook on its head. What if the speed of light wasn't constant back then? The variable speed of light theory suggests that in the universe's earliest moments, light traveled far faster than its current limit of 186,000 miles per second. This wouldn't just rewrite the rules, it would redefine how quickly matter could collapse into black holes, supercharging their growth. Imagine a cosmic cheat code where gravity operated on overdrive, compressing matter into supermassive seeds almost overnight. But there's another twist. ULA's J1342+0928 isn't alone. Dozens of similar early quasars now dot the cosmic map, each defying conventional timelines. Some theorists argue these black holes didn't grow slowly by swallowing gas. Instead, they might have gorged on entire stars in a single bite. In the dense, chaotic environment of the young universe, direct collisions between massive objects could have funneled stupendous amounts of matter into these gravitational pits, bypassing the usual slow and steady feeding mechanisms. Then there's the wild card primordial black holes. These hypothetical relics from the Big Bang itself could have served as ready-made seeds, some already weighing thousands of solar masses from birth. If they existed, they'd provide the head start needed to explain these impossible early giants. The James Webb Space Telescope is now hunting for clues, peering deeper into the cosmic dawn than ever before. Every new quasar it discovers pushes the mystery further. The universe seems to have crafted its most massive structures far sooner than we ever thought possible. What makes ULA's J1342+0928 so mesmerizing isn't just its defiance of physics, it's the questions it leaves hanging. Was the early universe a place where the laws of nature flexed and bent in ways we can't yet replicate? Or are we missing something even more fundamental? A hidden chapter in the story of how cosmic structures emerge. The answers, if they come, won't just solve the puzzle of impossible quasars, they'll reshape our understanding of time, gravity, and the very fabric of reality. Black holes aren't supposed to have table manners, so why is one of the universe's most voracious eaters exhibiting something that looks suspiciously like cosmic indigestion? Meet Assassin 14 Co., a galaxy 140 million light-years away with a supermassive black hole that's been flashing like a malfunctioning neon sign. Every 114 days, like clockwork, its brightness spikes dramatically before fading back to normal. This rhythmic flickering defies the usual chaotic feeding patterns of black holes, presenting astronomers with a delicious puzzle. What could possibly cause such precise, repeating outbursts from an object that's supposed to devour matter at random? The leading explanation involves a star trapped in an elliptical death spiral. Unlike most tidal disruption events where a star gets too close and is shredded in a single, catastrophic meal, Assassin 14 Co. might showcase a more drawn-out process. Picture a cosmic game of chicken where a star skims perilously close to the black hole on each orbit, losing chunks of its gaseous outer layers without being fully destroyed. Each close pass would trigger a fresh flare as stellar material rains down onto the accretion disk, creating those predictable bursts of light, the 114-day interval. That's likely the star's orbital period, ticking like a slow-motion metronome counting down to its eventual demise. But there's another compelling possibility, a warped, wobbling accretion disk. Supermassive black holes don't just pull in matter, they spin, and that rotation can twist their surrounding disks into precessing, lopsided shapes. If part of the disk periodically tilts toward Earth's line of sight, it could explain the regular bursts as hotter, brighter regions swing into view. This lighthouse effect would make the black hole appear to hiccup without any actual change in its feeding rate, an illusion of perspective rather than a true physical cycle. What makes Assassin 14 Co. particularly fascinating is its persistence. While most tidal disruption events flare once and fade, this one has maintained its rhythm through over a dozen observed cycles. Some calculations suggest the star might survive another decade before finally being torn apart, offering astronomers an unprecedented opportunity to study a slow-motion cosmic demolition. Other galaxies show similar periodic flares, hinting that this might be a common but previously overlooked phase in black hole feeding behavior. The implications stretch far beyond one peculiar object. If precessing disks are responsible, they could reveal hidden details about black hole spins, a property notoriously difficult to measure. Alternatively, if multiple stars are caught in similar death spirals across the universe, they might serve as standard candles for measuring cosmic distances with unprecedented precision. Every flicker from Assassin 14 Co. carries encoded information about the brutal physics governing our universe's darkest corners. As observatories like the Vera Rubin Legacy Survey of Space and Time come online, they'll scan millions of galaxies for these telltale flashes, potentially uncovering a whole population of black holes with hiccups, each one ticking like a cosmic clockwork bomb. Deep in the cosmic void, something unseen is pulling. Hundreds of thousands of galaxies, including our own Milky Way, are racing toward a mysterious patch of sky at 14 million miles per hour, a force so immense scientists call it the Great Attractor. This gravitational anomaly lies hidden behind the dusty plane of our galaxy, obscured from direct view. But what could possibly wield such power over an entire supercluster of galaxies? Some suspect not one, but an entire swarm of supermassive black holes lurking where light cannot reveal them. The leading theory suggests the Great Attractor is actually the core of the Laniakea supercluster, a vast cosmic web where galaxies flow like rivers toward its dense central region. At its heart lies the Norma cluster, packed with massive elliptical galaxies, each potentially hosting their own supermassive black hole. Combined, their gravitational influence could explain the relentless pull we observe. It's like standing in a valley surrounded by invisible giants, each tugging you forward with unseen hands. But there's a problem. Even when accounting for all visible matter in the region, the math doesn't quite add up. The Great Attractor's pull is stronger than the combined mass of known galaxies should allow. This discrepancy has led to a radical alternative, dark flow. Some cosmologists propose the motion isn't caused by a nearby concentration of mass at all, but rather by the gravitational influence of structures far beyond our observable universe. Picture a cosmic undertow where the invisible bulk of entire superclusters outside our visible horizon drags everything toward it like an interstellar riptide. Recent X-ray observations add fuel to the black hole hypothesis. The region emits strange, diffuse radiation that hints at hot gas compressed by powerful gravitational forces, exactly what you'd expect if multiple supermassive black holes were stirring the cosmic pot. Even more intriguing, some simulations suggest black holes born in the early universe could have migrated into these dense knots over billions of years, stacking up like marbles in a bowl until their combined gravity reshaped the motion of galaxies on a staggering scale. The debate isn't just academic. If dark flow is real, it implies our universe is far more asymmetric than we thought, with structures so massive they bend the rules of cosmology itself. But if hidden black holes are the culprit, it would mean these gravitational monsters don't just dominate their own galaxies, they can choreograph the dance of entire superclusters. Future telescopes like the European Space Agency's Euclid mission aim to map these invisible influences in unprecedented detail. Until then, the great attractor remains one of the cosmos' most tantalizing enigmas. A reminder that even as we peer deeper into space, some of its most powerful players might still be hiding in the shadows. Some black holes don't play by the rules, they get kicked out of their galactic homes entirely, sent flying across the cosmos at speeds that defy imagination. Take 3C186, a supermassive black hole caught in the act of escaping its own galaxy at 7.5 million miles per hour. That's fast enough to travel from Earth to the Moon in under 3 minutes. This cosmic runaway wasn't born wandering, it was violently ejected, a consequence of one of the universe's most extreme events, a galaxy collision so brutal it sent a black hole packing. The physics behind this intergalactic eviction notice is as fascinating as it is violent. When two galaxies merge, their central black holes eventually spiral toward each other, locked in a gravitational dance that ends with a cataclysmic collision. But here's where Einstein's relativity throws a curveball. As these black holes merge, they don't just combine quietly. The energy released in the form of gravitational waves isn't perfectly symmetrical. If one black hole spins faster or at a tilted angle compared to its partner, the resulting gravitational wave burst can act like a cosmic rocket engine, kicking the newborn black hole clear out of the galaxy. LIGO, the Laser Interferometer Gravitational Wave Observatory, has detected these recoil effects in smaller black hole mergers, but supermassive ones like 3C186 take the phenomenon to an entirely new scale. What makes 3C186 so special isn't just its speed, it's the smoking gun it left behind. Hubble Space Telescope images reveal a quasar, the bright signature of an actively feeding black hole, positioned bizarrely far from its host galaxy's center. Even more telling, a vast arc of glowing gas stretching between the galaxy and the quasar, like a cosmic breadcrumb trail marking the black hole's path of escape. This isn't just theoretical, it's direct evidence of a supermassive black hole caught in the act of going rogue. The implications ripple far beyond a single runaway. If black holes can be ejected this easily, it means galaxies might lose their central anchors more often than we thought. Some could even wander the void indefinitely, drifting between galaxies like cosmic nomads, their presence detectable only if they happen to feed on interstellar gas along the way. Others might eventually slow down, settling into a lonely orbit in intergalactic space, invisible to all but the most sensitive telescopes. Yet the biggest question remains, how many more are out there? Current estimates suggest up to 10% of supermassive black holes could be ejected during mergers, meaning hundreds, perhaps thousands, might be lurking in the darkness between galaxies, invisible except for the rare occasions when they light up as quasars. Future observatories like LISA, the Laser Interferometer Space Antenna, aim to detect the gravitational waves from these colossal mergers directly, potentially catching more black holes in the act of being flung into the abyss. Until then, 3C186 stands as a breathtaking reminder that even the universe's most massive objects aren't immune to cosmic eviction, and that gravity's reach can sometimes be as violent as it is inexorable. At the heart of Galaxy M87, a cosmic fire hose blasts matter across 5,000 light-years, a jet so powerful it outshines the entire Milky Way. These relativistic jets, fueled by supermassive black holes, defy intuition. How can objects famous for sucking matter also become the universe's most efficient particle accelerators? The answer lies in twisted magnetic fields, spinning faster than the black holes themselves, wrenching plasma into beams that stab through galaxies at 99% the speed of light. What makes these jets truly bizarre are their helical structures, corkscrew patterns etched into the streaming plasma like celestial barber poles. Chandra X-ray observatory images reveal tightly wound magnetic coils stretching far beyond the black hole's immediate surroundings, a phenomenon that shouldn't persist over such distances. Picture trying to twist a rubber band around your finger, then stretching it across a football field without it snapping. According to standard magnetohydrodynamics, these spirals should dissipate within light years, yet they hold their shape for millions. Some theorists propose the answer lurks in the black hole's ergosphere, the warped space just outside the event horizon where frame dragging spins space-time itself into a whirlpool. Here, magnetic field lines get stretched like taffy, storing colossal energy before snapping violently, launching plasma into the jet with enough force to etch those enduring helices into intergalactic space. Even more perplexing is the particle acceleration. The electrons in M87's jet radiate gamma rays with petaelectronvolt energies. That's 1,000,000 billion electron volts, far beyond what any human-made collider could produce. Traditional shock acceleration models can't explain such extreme energies over these scales. One radical solution involves magnetic reconnection events, cosmic short circuits where tangled field lines explosively reorganize, converting magnetic energy directly into particle acceleration. It's like snapping a rubber band repeatedly to heat it up, except here the rubber band is light years wide, and the snap unleashes energies rivaling supernova. The Ice Cube Neutrino Observatory might have already caught evidence of this process, detecting high-energy neutrinos aligned with the jet's direction, hinting at proton acceleration happening alongside the electrons. Yet the greatest mystery remains the jet's stability. Simulations show these beams should instigate turbulence and dissolve within millennia, yet M87's jet has persisted for tens of millions of years. Some researchers speculate the black hole's spin acts as a gyroscopic stabilizer, its precise alignment preventing wobble. Others suggest an unseen feedback loop, where the jet itself regulates its own magnetic fields, creating a self-correcting system. If true, it would mean these aren't just mindless eruptions. They're finely tuned cosmic engines operating on principles we've only begun to decipher. Every new observation peels back another layer of complexity. Recent radio interferometry caught the jet flickering in sync with X-ray flares from the black hole's accretion disk, proving the connection is more dynamic than anyone assumed. Meanwhile, the Event Horizon Telescope's follow-up studies reveal substructures within the jet base, mini-jets spiraling within the main flow like tributaries in a river. These features suggest acceleration happens in multiple stages, with particles gaining energy in bursts rather than steadily. It's a messy, violent process that challenges textbook models of astrophysical jets. What emerges is a picture of terrifying elegance, black holes not as simple destroyers, but as architects of some of the universe's most intricate energy channels. Their jets don't just pierce galaxies, they seed them with high-energy particles that might trigger star formation, influence galactic magnetic fields, and even deliver the raw ingredients for life across cosmic distances. Far from being anomalies, these magnetic monsters might be the unseen regulators of galactic ecosystems, their invisible hands shaping the universe on scales we're only beginning to map. As next-generation telescopes like the Square Kilometre Array come online, they'll trace these jets in unprecedented detail, potentially revealing whether they're cosmic accidents or the universe's preferred method of energy distribution. Until then, each helix, each gamma-ray flare, each neutrino whisper from these jets forces us to reconsider how black holes don't just consume the cosmos, they actively shape it. Stephen Hawking's most controversial idea wasn't about how black holes behave, it was about what happens when they die. In 1974, he dropped a bombshell. Black holes slowly evaporate, leaking radiation until they vanish entirely. But here's the catch: Hawking claimed this radiation carried no information about the matter the black hole had swallowed. In other words, everything that ever fell in stars, planets, even the universe's secrets, would be erased from existence when the black hole finally popped out of reality. This revelation sparked a 40-year battle with fellow physicist Leonard Susskind, a war over one of science's most fundamental principles. Information can never be truly destroyed, only scrambled. If Hawking was right, quantum mechanics itself would need rewriting. Susskind struck back with the holographic principle, a radical notion that the information wasn't lost, it was smeared across the black hole's event horizon like cosmic graffiti. Picture a library burning down, but the contents of every book magically imprinting themselves onto the smoke rising from the flames. This seemed mathematically sound, but it led to an even wilder implication. Two copies of reality might exist simultaneously, one inside the black hole, one encoded on its surface. The universe, it seemed, kept backup files. Then things got really strange. In 2012, the firewall paradox emerged. If information really was preserved at the event horizon, quantum theory demanded an inferno of high-energy particles there. A literal wall of fire that would incinerate anything crossing it. This contradicted Einstein's general relativity, which insisted falling into a black hole should feel like nothing at all until tidal forces took over. Suddenly, physicists faced an impossible choice. Either quantum mechanics or relativity had to break down at the horizon. The latest twist comes from ER equals EPR, a theory so elegant it could bridge the divide. Proposed by Juan Maldacena and Susskind, it suggests entangled particles, those spooky quantum twins that mirror each other instantly across any distance, might be connected by microscopic wormholes called Einstein-Rosen bridges. Apply this to black holes, and suddenly the information isn't lost or burned, it's transmitted through hidden tunnels in spacetime itself. Imagine tossing a book into a black hole, only for its contents to reappear chapter by chapter in another universe via quantum entanglement's backdoor. Yet mysteries remain. If ER equals EPR is correct, it implies black holes might not be cosmic dead ends after all, but back alleys in a vast multiverse network. Recent experiments with quantum computers have simulated toy versions of these wormholes, showing information can indeed traverse them intact. But the real test comes with gravitational wave astronomy. Future detectors might spot subtle echoes in black hole mergers, the signature of information slipping through microscopic wormholes rather than vanishing forever. What started as an abstract debate now holds existential weight. If information can be destroyed, reality itself might be less solid than we think, a temporary pattern in an ephemeral universe. But if it persists, hidden in wormholes or holograms, then black holes become something far stranger than graves. They're cosmic transformers, reshaping matter and memory into forms we're only beginning to decode. The paradox isn't just about physics, it's about whether the universe forgets or remembers everything. For decades, the no-hair theorem stood as gospel in black hole physics, the idea that these cosmic monsters could be described by just three simple properties: mass, spin, and charge. Everything else, the type of matter they swallowed, their formation history, even the quantum states of particles that fell in was supposedly erased forever. But in 2022, a bombshell mathematical proof turned this dogma on its head. The quantum hair conjecture suggests black holes might carry intricate quantum imprints after all, preserving information in subtle spacetime distortions around their event horizons. It's as if black holes don't just have 3 crew cuts but an entire head of quantum frizz. This revelation stems from an unexpected source: gravitational wave echoes. When LIGO detects black hole mergers, the signals usually match Einstein's predictions perfectly. A rising chirp as the black holes spiral together, followed by a clean ring-down as they settle into a single object. But buried in the noise of some events, like the 2019 merger catalogued as GW1 90521, researchers found faint but statistically significant echoes repeating at precise intervals. These shouldn't exist if black holes are perfectly smooth, as the no-hair theorem suggests. Instead, they hint at microscopic structures near the event horizon, quantum hairs that scatter gravitational waves like imperfections in a mirror. The math behind quantum hair is as elegant as it is radical. General relativity treats spacetime as a smooth fabric, but quantum mechanics insists it must have graininess at microscopic scales. Near a black hole's event horizon, this quantum foam could imprint itself into gravitational fields, preserving information about everything that crossed it. Picture dipping a sponge into ink. The sponge's structure determines how the ink distributes, creating a unique pattern you could decode if you knew how to look. Similarly, a black hole's quantum hairs would encode information in the way they warp spacetime, forming a kind of cosmic fingerprint. What makes this so revolutionary isn't just the physics, it's the implications for the infamous information paradox. If quantum hairs exist, they might resolve Hawking's dilemma by preserving information without requiring firewalls or holograms. Recent simulations from the University of Sussex show these hairs could form fractal-like structures around black holes, with gravitational echoes carrying distinct signatures of whatever fell in. A star made mostly of hydrogen would leave different echoes than one rich in iron, for example, meaning black holes might not be the ultimate shredders we thought they were. The most tantalizing evidence comes from supermassive black holes. Unlike their stellar mass cousins, these giants have event horizons large enough that quantum effects could manifest on observable scales. 2023 studies of Sagittarius, a star's gravitational wave background, revealed peculiar fluctuations that align with predictions for quantum hair. It's early days, but if confirmed, it would mean every supermassive black hole is effectively a cosmic hard drive, its surface etched with quantum data from billions of years of cosmic history. Not everyone's convinced, of course. Critics argue these echoes could be noise or artifacts of imperfect detection. Others point out that quantum hair would require modifications to Einstein's equations at scales we've never tested. But the stakes couldn't be higher. If black holes truly have quantum hair, it would bridge the last great divide between general relativity and quantum mechanics, potentially revealing a deeper theory of quantum gravity. Future gravitational wave detectors, like the planned Einstein telescope, aim to settle the debate by hunting for these echoes with unprecedented precision. Until then, the quantum hair conjecture remains one of the most thrilling and contentious ideas in modern physics, proving even the universe's darkest objects might not be as bold as we once thought. Black holes might seem like the ultimate destroyers, but in the Phoenix cluster, they're playing an unexpected role: cosmic midwives helping birth new stars at a staggering rate. This galaxy cluster, 7.7 billion light-years away, hosts one of the most extreme starburst regions ever discovered, with stars forming at nearly 20 times the Milky Way's pace. The twist: this stellar baby boom appears to be fueled by the supermassive black hole at the cluster's core, its violent outbursts creating conditions ripe for star formation instead of snuffing it out. It's a cosmic paradox. The same forces that typically strangle galaxies might, under the right conditions, become their greatest benefactors. The Phoenix Cluster's black hole doesn't behave like most of its kind. Typically, when a supermassive black hole feeds, it unleashes jets and radiation that heat surrounding gas to millions of degrees, preventing it from cooling and collapsing into stars, a process called quenching. Astronomers see this everywhere, from nearby elliptical galaxies to distant clusters. But in Phoenix, something extraordinary happens. The black hole's outbursts are powerful enough to carve enormous cavities in the hot gas. Yes, but then, like a gardener tilling soil, those shocks trigger turbulence that actually helps pockets of gas cool faster. Picture blowing on a spoonful of hot soup. Normally, the breath would scatter the steam, but here, the gust somehow makes droplets condense instead. Chandra X-ray observatory data reveals the mechanism in action. As the black hole's jets plow through the cluster's gas, they create vast shock waves that compress the surrounding material into dense, cold filaments. These filaments, rich in molecules like hydrogen, then collapse under their own gravity, igniting bursts of star formation along their lengths. ALMA radio telescope observations caught these stellar nurseries in stunning detail, rivers of gas hundreds of thousands of light-years long, glittering with newborn stars. It's as if the black hole's fury carved channels in a cosmic desert, only for those trenches to unexpectedly fill with water and sprout life. The implications rewrite our understanding of galactic ecosystems. Most models treat black hole feedback as purely destructive, a universal off switch for star formation, but Phoenix proves the reality is far more nuanced. The key seems to lie in the balance between heating and cooling. In most clusters, black hole outbursts overwhelm the system, keeping gas too hot to settle. Phoenix, however, sits in a sweet spot. Its black hole is active enough to stir the pot, but not so violent that it boils everything away. The cluster's dense core gas can still radiate heat efficiently, allowing rapid cooling once turbulence kicks in. It's a delicate dance, one that might explain why extreme starbursts like this are rare. Even more intriguing, this process could solve a long-standing cosmic mystery: how the universe's most massive galaxies formed their stars so quickly in the early cosmos. Astronomers have struggled to explain how galaxies like CR7, a behemoth in the young universe, could produce stars at rates hundreds of times higher than modern galaxies. If Phoenix-like black hole feedback was more common in the denser, gas-rich early universe, it might have acted as a natural accelerator, turning black holes into unlikely star-making machines. Future observations with the James Webb Space Telescope could test this by searching for similar cold gas filaments around ancient quasars. What happens in Phoenix doesn't stay in Phoenix. This discovery hints at a universal principle waiting to be uncovered. Black holes, it seems, aren't just agents of chaos or order, but cosmic regulators capable of both, their influence shifting with environment and scale. The same outburst that quenches star formation in one galaxy might ignite it in another, all depending on the delicate interplay of energy, density, and time. It's a reminder that even the universe's most fearsome monsters can sometimes play the hero, a twist that keeps astrophysics endlessly surprising. Andromeda, our closest galactic neighbor, should be a roaring beast. At its heart sits a supermassive black hole with a mass 40 times greater than Sagittarius, a star, our Milky Way's own cosmic heavyweight. Yet this colossal monster is eerily silent. No brilliant jets, no swirling accretion disk, just a faint whisper of activity that defies expectations. If our galactic center is a dormant volcano, Andromeda's appears buried under ice. This cosmic quiet has astronomers scrambling for answers. Why is such a massive black hole barely flickering, and what secrets does its silence hold? The most obvious explanation is starvation. Black holes shine when they feed, their accretion disks heating to millions of degrees as gas and dust spiral inward. But Andromeda's core shows a stunning absence of this cosmic buffet. Hubble Space Telescope observations reveal a shockingly clean neighborhood around the black hole, almost no loose gas or stars close enough to be torn apart. It's like finding a banquet hall with tables set but no guests in sight. Some researchers suspect Andromeda's turbulent past might be to blame. Galactic collisions can fling material toward the center, but they can also slingshot it away. Computer simulations suggest Andromeda's last major merger, around 2 billion years ago, could have cleared its central region like a cosmic vacuum cleaner, leaving its black hole to starve. But there's a twist: Andromeda might not be as dormant as it seems. In 2017, NASA Chandra X-ray Observatory caught an unexpected flare from the black hole, suddenly brightening by a factor of 100 before fading back to obscurity. This wasn't the signature of a star being torn apart. It was too brief, too clean. Instead, it matched predictions for what astronomers call a chaotic accretion event, a lone gas cloud drifting too close and vanishing in a quick gulp. These sporadic snacks suggest Andromeda's black hole isn't dead, just napping, waiting for the next cosmic meal to wander by. Then there's the missing disk mystery. Even quiet black holes usually have some residual accretion, a thin haze of infalling material. Andromeda's appears to lack even this. One radical theory proposes its magnetic field has become unusually strong, acting like an invisible force field that deflects incoming gas. Picture trying to fill a bucket during a hurricane. Most of the water gets blown sideways before reaching the bottom. Alternatively, the black hole might be in a phase where it consumes matter so efficiently that almost nothing radiates outward. Some models suggest supermassive black holes can enter advection-dominated states where gas falls in almost silently, like water circling a drain without a splash. The most tantalizing clue comes from Andromeda's past. Studies of its globular clusters, dense groups of ancient stars, reveal chemical signatures suggesting the galaxy's core was once ablaze with quasar-like activity billions of years ago. This means Andromeda's black hole might not be permanently quiet just between outbursts. Our Milky Way likely went through similar cycles. Sagittarius, a star, shows evidence of a violent eruption just 2 million years ago, a blink in cosmic time. The difference: our black hole appears to be waking up while Andromeda's remains in deep hibernation. What makes Andromeda's silence so fascinating isn't just the mystery, it's the implication that supermassive black holes might spend most of their lives in standby mode. Active, shining phases could be the exception rather than the rule, brief interludes in an otherwise quiet existence. Future telescopes like the European Extremely Large Telescope aim to study Andromeda's core in unprecedented detail, searching for subtle signs of movement in the void. Until then, this sleeping giant serves as a cosmic reminder. Sometimes the universe's most powerful objects choose to whisper rather than roar. Even the hungriest monsters eventually hit a limit, and for some of the universe's most voracious black holes, that moment comes abruptly. Take H1 821 plus 643, a quasar 9 billion light-years away that's devoured enough gas to reach 30 billion solar masses. Yet despite swimming in a sea of fresh material, this cosmic heavyweight has mysteriously stopped growing. It's as if a competitive eater suddenly pushed away from an all-you-can-eat buffet mid-meal, leaving scientists puzzled over what could possibly curb such insatiable gluttony. Radiation pressure might be the universe's built-in diet plan. As gas spirals toward a black hole, friction heats it to millions of degrees, creating intense light that pushes outward. Normally, gravity wins this tug-of-war, but for the most massive black holes, there's a tipping point. The photons they produce become so energetic they literally blow the dinner plate clean away. Picture trying to spoon soup into a blender set on high. Eventually, the splashing overwhelms your efforts. For H1 821 plus 643, its own brilliance may have starved it, creating a feedback loop where radiation clears its feeding zone faster than gravity can replenish it. But light isn't the only force at play. Magnetic fields, those invisible cosmic puppet strings, could be yanking the meal out of reach. Simulations of supermassive black holes show their magnetic fields don't just shape jets, they can also act like brakes on a spinning disk, flinging gas outward in colossal loops. ULMA telescope observations of nearby quasars reveal this phenomenon in action, with magnetic arcs slingshotting material hundreds of light years away. It's a cosmic version of swirling wine in a glass too vigorously, only to watch it spill over the rim. Then there's the most unsettling possibility: black holes might simply get full. The saturated accretion hypothesis suggests these giants could hit an internal limit where their space-time structure can't accommodate more infalling matter smoothly. Beyond a certain mass, the chaotic turbulence near the event horizon might become so extreme that incoming gas gets stuck in a traffic jam, circling endlessly like cars around a roundabout with no exits. X-ray monitoring of stalled quasars supports this idea, showing oddly stable disks where gas piles up without progressing inward, like a conveyor belt suddenly frozen in place. What makes H1821 plus 643 particularly fascinating is how it defies expectations. Most quasars slow down gradually as they exhaust local gas, but this one slammed on the brakes while still surrounded by fuel. Some researchers propose it crossed a critical threshold where its gravity began warping the fabric of spacetime so severely that the usual rules of accretion no longer apply. Others speculate it might be evidence of a hidden population of maxed-out black holes, cosmic titans that have hit the ultimate growth ceiling. The implications ripple across cosmology. If the largest black holes self-regulate, it could explain why we rarely see quasars exceeding 30 billion solar masses despite 13 billion years of potential feeding time. Future telescopes like the Vera Rubin Observatory aim to hunt for more of these stalled giants, testing whether they cluster around a specific mass range. Every discovery pushes us closer to answering one of astrophysics' most perplexing questions. In a universe of infinite appetite, why do the hungriest mouths eventually stop eating? The answer might rewrite not just our understanding of black holes, but the fundamental limits of cosmic growth itself. The universe is humming, a deep, seismic thrum vibrating through the very fabric of spacetime itself. In 2023, the Nanograv collaboration detected this cosmic murmur after 15 years of meticulous pulsar observations, revealing a gravitational wave background that permeates the cosmos. Unlike the sharp chirps from colliding stellar mass black holes detected by LIGO, this is a low-frequency drone, a nanohertz hum so deep it takes light years just to complete a single oscillation. The source, likely the combined ripples from millions of supermassive black hole pairs, locked in slow-motion mergers across the universe. Imagine dropping pebbles into a pond at random intervals. Each splash sends out circular waves that eventually overlap into a chaotic interference pattern. Now scale that up to galactic proportions, where the pebbles are black holes billions of times the sun's mass, and the pond is spacetime itself. These titanic duos don't collide quickly. They spiral together over millions of years, their orbital decay generating gravitational waves with wavelengths so vast they could stretch from Earth to Pluto and back. The result is a cosmic chorus, a superposition of countless inaudible notes blending into a detectable hum. What makes this discovery revolutionary isn't just the detection, it's what the signal reveals about black hole evolution. The amplitude of the background hum suggests supermassive black holes merge far more frequently than simulations predicted. Some theories argued these giants would stall just light years apart, trapped in what's called the final parsec problem, as they ran out of stars and gas to shed their orbital energy. But the gravitational wave background tells a different story. They're finding a way, whether through interactions with third black holes, circumbinary disks, or dark matter halos. It's as if the universe has hidden highways guiding these monsters together, and we're just now sensing the vibrations from their cosmic traffic. The pulsars themselves are the heroes of this story. These ultra-precise cosmic clocks, spinning hundreds of times per second, act as a galaxy-sized detector. As gravitational waves pass between Earth and a pulsar, they subtly stretch and compress space-time, causing the pulsar's rhythmic radio beats to arrive a few nanoseconds early or late. Nanograv's network of 68 pulsars across the Milky Way became the equivalent of a gravitational wave seismograph, catching those minuscule timing shifts buried under 15 years of data. The statistical significance over 4 sigma means there's only a 1 in 15,000 chance the signal is random noise. Yet mysteries linger. While supermassive black hole binaries are the leading explanation, alternative sources could contribute to the hum. Cosmic strings, hypothetical defects in spacetime left over from the Big Bang, might vibrate at similar frequencies if they exist. Even more speculative is the idea of primordial black holes, those potentially forged in the universe's first second, collectively merging in the darkness. Future observations will hunt for a telltale pattern called the Hellings-Downs curve, a specific angular correlation between pulsar pairs that would confirm the gravitational wave origin. This isn't just about hearing the universe's background noise, it's about decoding a new language of cosmic history. The amplitude and frequency spectrum of this hum could reveal the mass distribution of supermassive black holes across cosmic time, offering clues to how they grew so big so fast. Upgraded pulsar timing arrays and space-based detectors like LISA will soon turn this murmur into a symphony, each note carrying secrets about the universe's most enigmatic giants. We're not just listening to black holes, we're hearing the echo of galaxies stitching themselves together across billions of years. Galaxies should be screaming with activity, supermassive black holes at their cores devouring matter, spewing jets of energy, lighting up the cosmos as brilliant quasars. Yet when astronomers tally up these glowing beacons, the numbers don't add up. Surveys find only a fraction of the active galactic nuclei predicted by theory, leaving a glaring question: where are all the missing monsters? The answer might lie behind cosmic curtains of dust, or in the eerie silence of black holes biding their time. Thick cocoons of gas and dust could be hiding a vast population of supermassive black holes from view. Picture trying to spot a lighthouse during a sandstorm. Even the brightest beam gets smothered. Infrared and radio observations reveal what optical telescopes miss: galaxies shrouded in so much dense material that their central black holes are completely obscured. These buried quasars emit most of their energy at wavelengths our eyes can't see, their light absorbed and re-radiated by the surrounding dust. The James Webb Space Telescope recently peeled back these veils in stunning detail, uncovering black holes in galaxies previously classified as inactive. One striking example is NGC 1068, a seemingly ordinary spiral galaxy hiding a voracious black hole behind a dust torus so thick it blocks 99% of the emitted light. But dust isn't the only explanation. Some black holes might simply be sleeping. Active phases could be brief interruptions in an otherwise quiet existence, like volcanoes erupting only once every few millennia. Our own Milky Way Sagittarius, a star, exemplifies this currently dim, yet evidence suggests it flared dramatically just 2 million years ago, lighting up intergalactic clouds like a cosmic flashbulb. Computer simulations show these cycles depend on the chaotic availability of gas. A single star wandering too close might trigger a flicker of activity, while a major galactic collision could ignite a billion-year feast. The problem: we're catching most black holes during their long naps, missing the short bursts of brilliance in between. The most tantalizing clue comes from galaxy counts. While only 1 in 100 nearby galaxies hosts an obvious quasar, nearly all contain supermassive black holes when measured by their gravitational influence. This suggests the hidden majority isn't missing, just lurking. Some might be cloaked in dust, others fading from past outbursts, and a few perhaps caught in unusual feeding modes where matter falls in silently, like water swirling down a drain without a splash. The implications rewrite our cosmic census. If most supermassive black holes spend the bulk of their lives hidden or dormant, it means the universe's most powerful engines operate on schedules we're only beginning to decode. Future observatories like the Vera-Rubin telescope aim to catch these giants in transition, snapping portraits as they flicker awake or vanish behind fresh clouds of dust. Until then, the search continues for the monsters we can't see and the ones choosing for now to remain silent. Crossing the event horizon isn't just a point of no return, it's where time itself grinds to a halt. Picture an astronaut brave or foolish enough to dive toward a supermassive black hole. As they approach that invisible boundary, their wristwatch doesn't just slow down. From an outsider's perspective, the second hand freezes in place. Every signal they send, every desperate radio transmission or flashing beacon stretches into an infinite redshift, each pulse arriving farther apart until the final message lingers at the horizon for eternity, never quite reaching outside observers. It's not just death by spaghettification. It's an existential vanishing act where the astronaut's last moments are smeared across time like a cosmic film reel stuck on the same frame. But here's where relativity warps intuition even further. To the astronaut falling in, time passes normally, their watch ticks steadily, their heartbeat continues at its usual rhythm. The horror isn't in slow-motion disintegration. It's the realization that the entire future of the universe is rushing past them in what feels like minutes. As they cross the horizon, stars overhead streak and fade as eons of cosmic history flash by in seconds. Entire galaxies evolve, collide, and burn out before their eyes, the black hole's gravity bending time so severely that the outside universe becomes a time-lapse film on fast-forward. Their final moments might coincide with the heat death of the cosmos itself, all while they're still technically alive inside the black hole's embrace. Yet even this nightmarish scenario has a twist, frame dragging. Supermassive black holes don't just distort time, they wrench space-time around them like a spoon twisting through honey. Near a rapidly spinning black hole, the fabric of reality gets dragged along with the rotation, creating a vortex where space itself flows like a whirlpool. An astronaut near the poles might experience time dilation differently than one hovering above the equator, as if the black hole's spin stitches patches of time that run at mismatched speeds. The most extreme effects emerge in the ergosphere, the region just outside the event horizon where frame dragging becomes so violent that nothing can stand still, not even light. Here, time and space switch roles. Forward movement through time requires orbiting the black hole, as if the universe has tilted its axis. Matter caught in this zone gets slingshot to relativistic speeds, with some particles stealing energy from the black hole's rotation in a process so efficient it could power civilizations, if anyone dared to harness it. These aren't just abstract thought experiments. Observations of stars orbiting Sagittarius, a star reveal frame dragging in action, their path subtly perturbed by the black hole's spin. Future missions like LISA aim to measure these effects directly, using gravitational waves as probes. What looks like a static void from afar is actually a churning maelstrom of twisted spacetime, where the rules of cause and effect bend to the will of gravity's darkest architects. The closer we look, the clearer it becomes. A black hole's event horizon isn't just a boundary in space, it's a rift in time itself. Imagine the universe as a vast neural network, its threads of galaxies strung along filaments of dark matter like pearls on cosmic strings. At every intersection where these threads knot together, a supermassive black hole lurks not just as a passive resident, but as an active architect shaping the flow of matter across billions of light years. Illustrious TNG simulations, some of the most sophisticated cosmic models ever created, reveal these black holes as gravitational anchors in the cosmic web, their influence reaching far beyond their host galaxies to choreograph the dance of intergalactic gas. These simulations paint a startling picture. As primordial gas cools along the filaments of the cosmic web, supermassive black holes regulate the flow like cosmic floodgates. Their outbursts powerful jets and radiation heat surrounding gas, preventing runaway star formation in some regions while paradoxically triggering it in others. One stunning visualization shows a black hole's jet punching through a filament, creating shock waves that ripple through the gas like a stone dropped in a pond. The resulting turbulence stirs the primordial soup, mixing heavy elements forged in supernova back into the intergalactic medium, a recycling process crucial for future generations of stars and planets. The scale of this influence is staggering. A single active black hole can impact gas flows over distances 10 times larger than its host galaxy. In dense cluster environments, multiple black holes may even work in concert, their combined feedback creating vast bubbles of heated gas that rise through the cosmic web like balloons in water. These bubbles don't just drift aimlessly. Illustrious TNG shows they can redirect entire rivers of gas, starving some galaxies of fuel while delivering fresh material to others. It's a cosmic redistribution of wealth where black holes play the dual role of destroyers and benefactors. Recent observations back up these simulations. The eROSITA X-ray telescope has mapped hot gas structures in the cosmic web that align eerily with predicted black hole-driven outflows. One filament in the Pisces Cetus supercluster shows gaps coinciding with the positions of known quasars like bite marks taken out of the gas stream where black hole activity has carved voids. Even more compelling, ALMA telescope data reveals cold gas clouds condensing in the wake of these outflows, as if the black hole's violence inadvertently creates nurseries for future star formation. The implications rewrite our understanding of cosmic evolution. Rather than seeing supermassive black holes as mere byproducts of galaxy formation, we're now realizing they might be conductors orchestrating the growth of large-scale structure itself. Their outbursts could explain why the cosmic web isn't uniform, why some regions teem with galaxies while others stretch as empty voids. Future telescopes like the Square Kilometre Array aim to trace this hidden influence by mapping hydrogen flows across unprecedented volumes of space. Every new dataset brings us closer to answering a profound question. Are black holes the universe's way of weaving its own tapestry? The cosmic web may look delicate, but its threads are held taut by the darkest, most powerful objects in existence. Galaxies seem to thrive under a cosmic balancing act, their supermassive black holes neither too ravenous nor too dormant, but hovering in a mysterious Goldilocks zone where star formation and black hole activity reach perfect equilibrium. Take the nearby galaxy NGC 4536. Its central black hole isn't a quasar blasting radiation, nor is it entirely silent. Instead, it emits gentle pulses of energy, just enough to keep the surrounding gas slightly warm, preventing runaway cooling that would otherwise trigger chaotic starbursts. This delicate calibration defies expectation, as if some unseen cosmic thermostat regulates the system, maintaining conditions that are, in the words of one astronomer, not too hot, not too cold, but just right. The mechanism behind this balancing act lies in black hole feedback, a self-regulating cycle where the very energy that suppresses star formation also ensures its eventual rebirth. Here's how it works. When a black hole feeds vigorously, its outbursts heat surrounding gas, pushing it outward and temporarily starving both itself and the galaxy of fresh star-forming material. But as the outflow dissipates, the cooled gas eventually rains back down in a process astronomers call precipitation, reigniting star formation and providing new fuel for the black hole. In galaxies like NGC 4536, this cycle appears perfectly timed, creating rhythmic waves of activity rather than catastrophic booms or busts. Evidence for this cosmic metronome comes from stunning multi-wavelength observations. Ulma radio eyes have caught galaxies where cold gas flows inward like rivers feeding a lake, while Chandra's X-ray vision reveals hot bubbles inflated by black hole jets, the two phases coexisting in precarious balance. Simulations from the FIRE project show this isn't coincidental. The black hole's energy output automatically scales with the gas supply, like a pressure release valve in a steam engine. Too much feedback and the galaxy overcools into a red, dead elliptical. Too little and it becomes a disorganized starburst burning through its fuel too quickly. Yet mysteries remain. Some galaxies, like the iconic whirlpool, display patchy star formation, vibrant spirals in their outer arms, while their central black holes stay oddly quiet. Others, like Messier 87, show feedback so efficient it's created a nearly gas-free core spanning thousands of light years. The key difference might lie in the black hole's spin. Rapidly rotating monsters could funnel energy into narrow jets that penetrate far beyond their host galaxies, while slower spinning ones might distribute heat more evenly, creating the gentle turbulence that defines Goldilocks systems. The most tantalizing clue comes from cosmic dawn. Early galaxies forming stars at breakneck speed somehow avoided self-destruction, suggesting black hole feedback kicked in earlier and more precisely than models predict. JWST infrared gaze has spotted young quasars whose radiation appears fine-tuned, strong enough to regulate growth without sterilizing their environments. Whether by luck or some deeper physics, the universe seems biased toward equilibrium. Its black holes acting not just as destroyers, but as cosmic gardeners tending their galactic ecosystems with surprising finesse. This hidden harmony might answer one of astronomy's oldest questions: why so many galaxies, ours included, have enjoyed billion-year lifespans rather than flaming out in brief, spectacular bursts. The cosmos, it seems, has a knack for finding the sweet spot. The universe might meet its end not with a bang, but a rip, a catastrophic tearing apart of spacetime itself called the Big Rip. Theory suggests that if dark energy intensifies over time, eventually labeled phantom energy, it could accelerate cosmic expansion so violently that galaxies, stars, and even atoms would be shredded apart. But amidst this apocalyptic scenario, supermassive black holes could emerge as unlikely survivors, their event horizons acting as cosmic fortresses against the onslaught. Recent studies on vacuum decay the idea that our universe's quantum fields might destabilize hint at an eerie possibility. Black holes could feed on phantom energy itself. As spacetime stretches toward infinity, these gravitational giants might absorb the very force tearing the cosmos apart. Picture a whirlpool in an accelerating river. The current grows stronger, but the vortex deepens with it, swallowing the chaos rather than being swept away. Mathematically, as phantom energy's density increases, its negative pressure could funnel into black holes, effectively counteracting their evaporation through Hawking radiation. Instead of fading, they'd grow, their mass ballooning as they feast on the fabric of a disintegrating universe. The physics behind this is as counterintuitive as it gets. Normally, black holes lose mass by radiating particles at their horizons, a slow leak predicted by Hawking. But phantom energy flips the script. Its repulsive gravity would warp spacetime so drastically that incoming energy couldn't escape the black hole's grasp. Some models suggest this could trigger a runaway effect. The more phantom energy a black hole consumes, the larger its event horizon becomes, allowing it to capture even more energy. It's a cosmic feedback loop where the destroyer becomes the preserved, growing endlessly as everything else crumbles, but survival wouldn't mean safety. Isolated in a void where spacetime itself is fraying, these black holes would face a surreal fate. With no stars left to consume and no matter to accrete, they'd become the universe's final structures, cold, dark monarchs ruling over nothing. Quantum effects near their horizons might spark brief flickers of particle creation, tiny fires in an infinite night, but eventually even those would cease. The last black hole standing could be all that remains of a universe that once teemed with galaxies, life, and light. The most radical implication: these black holes might outlast time itself. In a Big Rip scenario, the very concept of before and after dissolves as space-time structure ruptures. Yet black holes, with their singularities where physics breaks down, could persist in some distorted form, not as the universe's gravestones, but as cryptic vaults holding information from a reality that no longer exists. Whether they'd endure the rip's final moments or merely delay the inevitable remains one of cosmology's most haunting questions. What began as theoretical curiosity now hints at a profound irony. The objects we once thought were nature's ultimate endpoints might instead be its final witnesses, clinging to existence long after the cosmos has torn itself apart. Future simulations aiming to model phantom energy interactions could reveal whether black holes truly are the universe's last hope, or merely its last flicker before eternal silence. Either way, their role in the cosmic endgame challenges everything we thought we knew about destruction, survival, and the limits of space-time itself. Black holes seem to come in two flavors: tiny ones forged from dying stars, and gargantuan beasts anchoring galaxies. But nature rarely leaves gaps this glaring, which makes the missing middleweights one of astrophysics' most persistent puzzles. Intermediate mass black holes, or IMB, should theoretically bridge the divide between stellar remnants and supermassive giants, yet conclusive sightings remain as elusive as shadows in a dark room. Take HLX-1, an X-ray beacon 30,000 times the Sun's mass lurking near the galaxy ISO 243-15. For years, it was the prime suspect, flaring with telltale accretion signatures, but even its classification sparked debates. Was it a true IMB, or just an unusually bright stellar mass black hole caught in a feeding frenzy? The hunt gets murkier when we consider how these middleweights might form. Unlike supermassive black holes that grow from seeds or mergers, IMB require a Goldilocks scenario: enough mass to surpass stellar limits, yet insufficient time or fuel to balloon into supermassive status. Dense stellar clusters like Omega Centauri offer promising nurseries here. Runaway collisions between massive stars could forge black holes of hundreds or thousands of solar masses through a chaotic game of gravitational bumper cars. Simulations show it's possible, but observational proof is frustratingly sparse. The best clues come from ultraluminous X-ray sources, or ULKs, which flicker with energies too high for stellar mass black holes yet too faint for supermassive ones. Objects like M82X1 flirt with IMB status, their X-ray pulses hinting at masses around 500 suns, but alternative explanations like beamed emission from smaller black holes keep the mystery alive. Then there's the question of survival. IMB should be gravitational bulldozers sinking to cluster centers over time, yet searches in globular clusters keep coming up empty. Some theorists propose these middleweights get kicked out during dynamical interactions, doomed to wander intergalactic space unseen. Others suggest they're gobbled up too quickly, serving as snacks for growing supermassive black holes. The few strong candidates we have, like the recently discovered gravitational wave event GW190521, hint at mergers between black holes in the so-called mass gap, collisions too hefty for stellar remnants, yet too petite for supermassive giants. Perhaps the most tantalizing possibility is that IMB are hiding in plain sight. Tidal disruption events, where stars are shredded by black holes, sometimes show energy profiles suggesting mid-sized predators. In 2020, the flare at 2020 JWST was attributed to a black hole of roughly 10,000 solar masses, its victim's death throes lighting up like a cosmic flare gun. Meanwhile, pulsar timing arrays are listening for the low-frequency hum of IMB binaries, their gravitational waves potentially revealing populations too dim to spot otherwise. The implications run deep. If Embark confirmed, they could solve multiple riddles at once, seeding early supermassive black holes, explaining ardulax emissions, and revealing a hidden chapter in black hole evolution. Their absence would be just as profound, forcing us to rethink how cosmic structures assemble across scales. Next-generation telescopes like LISA and the Extremely Large Telescope may finally close this gap, but for now, these missing middleweights remain both a frustration and a siren call, reminding us that even the universe's darkest objects can't hide their mysteries forever. Deep within the swirling chaos of an accretion disk, spacetime itself begins to tremble. These aren't the violent spasms of a star being torn apart or the explosive finale of a black hole merger. They're subtler, rhythmic vibrations called quasi-periodic oscillations, or QPO. Imagine the deep, resonant hum of a plucked guitar string, but scaled up to cosmic proportions where the string is the fabric of reality warped by a black hole's immense gravity. NICA telescope, mounted on the International Space Station, has become our most sensitive stethoscope for listening to these spacetime earthquakes, uncovering patterns that could reveal black holes' innermost secrets. What makes QPOs so fascinating is their clockwork precision amidst the chaos. Like seismic waves traveling through Earth's layers, these oscillations ripple through the hot gas orbiting a black hole at nearly light speed. Some pulse hundreds of times per second, their frequencies locked to the black hole's spin like a cosmic metronome. Others emerge slower, resonant echoes of matter falling toward the event horizon. The NICA data reveals an astonishing hierarchy. Multiple QPOs often overlap, creating interference patterns akin to musical harmonies. A black hole weighing millions of suns might ring with the same mathematical purity as a struck bell, its tone determined by mass and rotation alone. The most striking discovery came from studying MAXI J1820+070, a stellar mass black hole gorging on a companion star. NICA caught not just one QPO, but an entire cascade high-frequency vibrations from plasma whipping around the innermost stable orbit, superimposed on lower-frequency waves from the accretion disk's outer edges. This multi-layered tremor matched predictions from Einstein's relativity with uncanny precision, as if the black hole were broadcasting its internal structure through space-time ripples. Scientists liken it to hearing a symphony where each instrument reveals a different layer of the orchestra. The piccolo's pitch hints at the room's dimensions, while the timpani's boom exposes the floor's material. Yet mysteries remain. Some QPOs flicker unpredictably, their frequencies drifting like a radio station losing signal. Others appear only during specific spectral states, phases where the accretion disk undergoes dramatic changes in temperature and density. The leading theory suggests magnetic fields play conductor, their lines snapping and reconnecting to drive these oscillations. Picture a whirlpool where underwater currents occasionally surge, creating rhythmic bulges in the water's surface. In a black hole's case, those currents are titanic magnetic forces, twisting the accretion disk like taffy until it vibrates in protest. What NICA has uncovered goes far beyond academic curiosity. QPOs might be the key to measuring black hole spins with unprecedented accuracy, a crucial metric for understanding how these objects evolve. Already, observations of the supermassive black hole in galaxy read J1034+396 suggest it's spinning at nearly 90% the speed limit set by physics. Future missions like the European Space Agency's Loft satellite aim to expand this research, potentially detecting QPOs from intermediate mass black holes, the elusive middleweights that could bridge stellar and supermassive varieties. The implications stretch into the surreal. If certain QPO patterns prove universal, they might form a cosmic language, a way for black holes across the universe to speak through vibrations in spacetime. Some theorists even speculate advanced civilizations could manipulate these oscillations artificially, using them to transmit information or navigate the warped geometry near event horizons. While that remains speculative, one truth is undeniable. The once silent voids we called black holes are actually humming with activity, their tremors carrying secrets we're only beginning to decode. Every flicker, every harmonic, every drifting frequency is a clue not just about the monsters producing them, but about the fundamental nature of space-time itself. Across the cosmos, countless galaxies glow with the energy of billions of stars, yet we hear nothing from them. No signals, no megastructures, no signs of cosmic neighbors. This eerie silence is the heart of the Fermi paradox, and supermassive black holes might hold a terrifying solution. They could be nature's ultimate great filter, systematically preventing civilizations from reaching the stars. Not by design, but through their sheer, inescapable physics. Consider the staggering energy needs of an advanced civilization. Any society progressing beyond planetary scales would inevitably seek power sources matching their ambitions. And what better battery than the gravitational dynamo of a black hole? Theoretical constructs like Dyson spheres seem quaint compared to the potential of tapping an accretion disk's furious energy or harnessing a spinning black hole's ergosphere through processes like the Penrose effect. But this very ambition might be their undoing. A single miscalculation while harvesting such power could trigger catastrophic feedback loops, overfeeding the black hole until its radiation sterilizes nearby space, or accidentally stabilizing its orbit to begin swallowing entire star systems. The evidence might already exist in galactic dead zones, regions like the Fermi Bubbles where superheated gas spans tens of thousands of light years. These could be ancient graveyards of civilizations that pushed too far, their energy projects gone awry. Worse yet, black hole-based computing, a hypothetical leap beyond quantum technology, might require operating perilously close to the event horizon. One errant fluctuation in space-time geometry could collapse the entire system into the singularity, taking entire civilizations with it. Yet an even darker possibility exists. Black holes may be universal attractors for self-destruction. The same physics making them irresistible power sources also makes them perfect weapons. A society capable of nudging a black hole's trajectory, say, by feeding it asymmetric jets, could wield it as a relativistic catapult, hurling gravitational singularities at enemy worlds. The aftermath of such conflicts wouldn't just eliminate civilizations. It would erase all evidence they ever existed, their ruins swallowed by the very engines they sought to control. This isn't mere speculation. Our own galaxy's core exhibits unexplained flares, brief, intense bursts that don't match natural models. Could these be signatures of long-vanished attempts at black hole engineering? The grim elegance of this solution to the Fermi paradox lies in its simplicity. Advancement doesn't just carry risk of self-destruction through war or pollution, but through the unavoidable appeal of tapping fundamental cosmic forces. The silence we perceive isn't because intelligence is rare, but because black holes, the universe's ultimate power sources, are also its most perfect traps. Perhaps this explains why we find ourselves orbiting a quiet star far from galactic centers. Our cosmic backwater location, once seen as a handicap, might be the sole reason we've avoided the fate of civilizations who gazed into the abyss and found the abyss gazing hungrily back. The idea that our three-dimensional universe might be a hologram, a projection from a two-dimensional surface, sounds like science fiction. Yet black holes are providing startling clues that this could be the fundamental nature of reality. It all hinges on a bizarre property first discovered by Jacob Bekenstein and Stephen Hawking. Black holes have entropy, a measure of disorder proportional not to their volume but to the area of their event horizons. This revelation shattered conventional thermodynamics. If a black hole's information content scales with its surface area rather than its volume, perhaps all information in the universe does too, like a cosmic pixel limit where the deepest truths are painted on spacetime's canvas rather than buried within it. Enter the holographic principle, a radical framework where the universe operates like a giant IMAX screen. The AD/S/CFT correspondence, a mathematical breakthrough by Horn-Maldacena, gives this wild idea concrete form. It proposes a perfect equivalence between a hypothetical higher dimensional space, anti-de Sitter space, and a lower dimensional quantum field theory on its boundary. Picture a sealed soda can where the physics of the bubbling liquid inside our apparent 3D reality is entirely encoded on the can's 2D surface. Black holes become the ultimate test case. Their event horizons behave like stretched membranes storing information in microscopic Planck-scale pixels, with each bit corresponding to a quarter of a Planck area. String theory calculations show this encoding isn't approximate but exact. Every particle falling in leaves a scrambled but recoverable imprint on the horizon surface. The implications rewrite physics from the ground up. Take quantum entanglement, the spooky connection between particles across vast distances. In the holographic view, these links might arise from deeper connections in the lower dimensional boundary theory, like threads stitching the cosmic projection together. Even gravity, traditionally seen as spacetime's curvature, could emerge holographically from quantum entanglement on the boundary. When two black holes entangle, they might form an Einstein-Rosen bridge, a wormhole connecting them through higher dimensional space, a phenomenon dubbed ER=EPR. This isn't just mathematical elegance. It suggests the fabric of reality is woven from information relationships rather than material substance. Critics argue the AD/S/CFT model describes an idealized universe with negative curvature, unlike our flat or positively curved cosmos. Yet recent advances in de Sitter holography hint at extensions to realistic cosmologies. The James Webb Space Telescope's deep field images, revealing universe-scale filamentary structures, intriguingly resemble neural networks, a visual echo of holographic organization. Meanwhile, lab experiments with quantum computers simulate toy versions of AD/S/CFT, observing entanglement patterns that mirror predictions. If black holes are nature's hard drives, their event horizons might be showing us the operating system of existence itself, a universe where depth is an illusion and everything that was, is, or will be is written on the surface of the ultimate void. Gravity should make black hole mergers inevitable, two cosmic titans spiraling closer until they collide in a burst of gravitational waves. Yet nature has built in a cosmic speed bump, the final parsec problem. When supermassive black holes draw within about 3 light-years of each other, their dance stalls as if the universe itself hit pause, the culprit. A simple but stubborn law of physics, angular momentum. Without external help, these black holes could orbit each other for billions of years, forever stranded just shy of collision. The dynamics behind this standoff reveal a delicate balancing act. As black holes circle, they shed energy by flinging stars away through gravitational slingshots, a process called dynamical friction. But as the orbit tightens, the available stars thin out, leaving insufficient material to further break their motion. Imagine two figure skaters pulling closer by throwing weights outward. Eventually, they run out of weights to throw. N-body simulations illustrate this starkly. Without intervention, paired black holes become stuck in a gravitational stalemate, their angular momentum trapped like a spinning top refusing to fall. But the universe has workarounds. Enter the third body solution, a star, gas cloud, or even another black hole passing close enough to steal excess angular momentum. Recent simulations from the Illustris TNG project show how chaotic interactions in galactic centers can provide these cosmic mediators. One stunning visualization depicts a stellar interloper zigzagging between the black holes, its gravitational nudges acting like a series of minute course corrections that gradually destabilize the orbit. Over millennia, these microscopic pushes accumulate into a decisive shove, driving the black holes across the parsec threshold where gravitational waves take over. Gas dynamics offer another escape route. When galaxies merge, their swirling reservoirs of interstellar gas can funnel toward the central black holes, forming a shared circumbinary disk. Hydrodynamic simulations reveal how spiral density waves within this disk create drag, sapping orbital energy like cosmic quicksand. The black holes carve out cavities in the gas, their motion generating swirling eddies that gradually sap their momentum. ALMA telescope observations of merging galaxies like NGC 6240 support this filaments of cold gas spiral toward the nucleus, providing the necessary braking force. The most extreme solutions involve higher-order chaos. Some models suggest hierarchical triples, 3 or more black holes interacting in a gravitational pinball game, can efficiently overcome the final parsec. In these scenarios, the famous three-body problem's instability becomes a feature, not a bug. Close encounters eject one black hole at high velocity while the remaining pair loses enough energy to merge. Hubble's discovery of wandering black holes in galaxy outskirts may be the smoking guns of such violent ejections. What makes the final parsec problem so fascinating isn't just the astrophysics, it's the observational implications. If merging black holes routinely stalled, the universe's gravitational wave background would sound different. Pulsar timing arrays like nanograv are now tuning into this cosmic hum, searching for the statistical signature of countless mergers either overcoming or succumbing to the parsec barrier. The answer could reshape our understanding of galactic evolution, revealing whether supermassive black holes grow primarily through mergers or by guzzling gas. Yet mysteries linger. Some galaxies, like Embark 231, appear to host double black holes separated by less than a parsec, defying the stall. Are they exceptions proving the rule or evidence of an undiscovered merger mechanism? The upcoming LISA mission aims to detect gravitational waves from these late-stage inspirals, potentially catching black holes in the act of cheating the final parsec. Until then, this cosmic traffic jam remains one of the most consequential puzzles in black hole dynamics. A reminder that even gravity's mightiest forces sometimes need a nudge to tip the scales. At the event horizon, reality itself might be tearing apart, not in the smooth, uneventful glide Einstein predicted, but in a seething maelstrom of quantum spikes. This is the firewall paradox, born from a simple but devastating revelation. If black holes preserve information as quantum theory demands, then crossing the horizon shouldn't be the gentle passage general relativity describes. Instead, it might resemble plunging into a Planck-scale minefield, where space-time fractures into fractal fangs of unimaginable energy. The math behind this nightmare stems from a clash between two irreconcilable truths. Quantum mechanics insists information can't be destroyed, so Hawking radiation leaking from black holes must carry scrambled data about everything they've swallowed. But Einstein's equations paint the horizon as benign, a place where tidal forces are negligible, meaning an astronaut wouldn't notice crossing it until gravity's grip became unbearable. Combine these ideas and logic implodes. For information to escape via Hawking radiation, the radiation must be entangled with both the black hole's interior and the distant universe, violating quantum mechanics' no cloning rule. The only escape, a fiery discontinuity at the horizon that severs these illicit entanglements, a firewall blazing at over 1 trillion degrees. Loop quantum gravity offers an even wilder vision. Here, spacetime isn't smooth but granular, with a foamy structure at scales 100 billion times smaller than an atom. Near a black hole's horizon, this quantum foam could erupt into fractal turbulence, each Planck-length fluctuation birthing microscopic black holes that instantly evaporate. Picture the horizon not as a clean boundary but as a frothing shoreline where spacetime itself boils, its energy density spiking to infinity. Some models suggest these fluctuations could manifest as detectable echoes in gravitational wave signals, subtle glitches betraying the fractal chaos beneath the apparent smoothness. The debate crystallized in 2013 when physicists Ahmed Olmary, Donald Maroff, Joe Pulczynski, and James Sully, collectively known as AMPS, laid out the firewall argument with mathematical precision. Their equations forced a brutal choice: either abandon Einstein's equivalence principle, which says free fall feels locally like floating in empty space, or admit quantum mechanics has a catastrophic flaw. The physics community fractured. Some, like Leonard Susskind, rallied behind holographic solutions where information is encoded on the horizon's surface, avoiding firewalls altogether. Others embraced soft hair, quantum imprints around black holes that could store data without incinerating infalling observers. Observational clues remain elusive but tantalizing. Gravitational wave detectors like LIGO might someday spot firewall signatures, anomalous high-frequency vibrations superimposed on merger signals. Meanwhile, quantum simulators using ultra-cold atoms are recreating black hole thermodynamics in labs, testing whether horizon-scale turbulence leaves measurable imprints. The most radical experiments propose using entangled particles to probe the black hole information paradox directly, though the energy scales involved make this a distant dream. Underlying this esoteric battle is a profound philosophical rift. Is space-time fundamentally smooth, as relativity assumes, or is it pixelated, flickering in and out of existence like a cosmic video game rendering only what's observed? Black holes, as always, are forcing us to choose between competing visions of reality, and the answer might redefine not just singularities, but the fabric of the universe itself. Could the universe's darkest objects become its most unlikely think tanks? The Boltzmann brain paradox, a thought experiment where consciousness arises randomly from quantum fluctuations, takes a surreal twist when applied to supermassive black holes. These cosmic leviathans distort time so severely that near their event horizons, billions of years pass in what would feel like moments. In such an environment, the improbable might become inevitable, a self-aware entity spontaneously assembling from chaotic particle interactions, only to dissolve moments later under tidal forces. The math behind this eerie possibility stems from statistical mechanics. In an infinite universe with enough time, every possible particle arrangement, no matter how unlikely, will eventually occur. Near a black hole, time dilation stretches fleeting quantum fluctuations into apparent eternities. A region where seconds stretch into eons could provide the temporal runway needed for random fluctuations to assemble complex structures, including a functioning mind. Picture a storm raging through a junkyard given infinite time. It might momentarily arrange debris into a working computer. Now scale that up to quantum fields warped by relativistic gravity, where spacetime itself becomes the junkyard and the storm is the seething vacuum energy at reality's foundation. Critics counter with entropy's relentless pressure. Black holes are the ultimate entropy maximizers, shredding order into chaos. Yet counterintuitively, their very efficiency might create pockets where low entropy states briefly crystallize. Analogies emerge from fluid dynamics. Even in turbulent whirlpools, transient vortices form stable patterns before dissolving. Similarly, a black hole's ergosphere, that warped region where spacetime is dragged irresistibly by rotation, could host fleeting islands of coherence amidst the chaos. The Penrose process shows energy can be extracted here. Might it also permit accidental complexity? The observational implications border on metaphysical. If Boltzmann brains flicker into existence near black holes, they'd likely vanish before influencing their surroundings. But their potential existence challenges fundamental assumptions. Is consciousness truly a biological phenomenon, or merely a temporary configuration of information? Some interpretations of quantum mechanics suggest observation itself shapes reality, raising the unsettling notion that a Boltzmann brain's brief awareness could, in principle, collapse quantum probabilities just as a human observer might. The paradox deepens when considering black hole evaporation. As Hawking radiation carries away a black hole's mass, its final moments involve a frenzy of quantum activity. In this frenetic end stage, the conditions for spontaneous consciousness might peak before vanishing entirely. Theoretical models of Planck-scale spacetime suggest microscopic black holes could briefly birth countless such entities in their dying microseconds, a statistical inevitability if the universe truly runs on infinite timelines. Yet the ultimate verdict may lie beyond empirical reach. These hypothetical minds would leave no fossils in spacetime, no detectable traces beyond philosophical unease. Their relevance emerges not from observability, but from the razor's edge they walk between physics and metaphysics, enforcing us to confront whether awareness requires biological substrate or merely the right information configuration. Black hole Boltzmann brains reveal how deeply intertwined consciousness and cosmology may truly be. The event horizon's edge might be where physics meets philosophy and where reality's nature hangs in the quantum balance. Quadrillion years from now, when the last stars have flickered out and galaxies are nothing but skeletal remnants, black holes will reign as the universe's final sentinels. In this distant, frigid epoch, long after dark energy has shredded the cosmic web into isolated voids, these gravitational titans will stand alone, their slow but inevitable decay marking the last meaningful events before existence itself dissolves into eternal silence. Yet even their demise won't be swift. A supermassive black hole with the mass of 1,000 suns could take 10 to the 92 years to evaporate, a time span so vast it dwarfs the current age of the universe by more orders of magnitude than there are atoms in the Milky Way. The process is as eerie as it is relentless. Hawking radiation, that faint quantum whisper at the event horizon, begins as a negligible trickle but accelerates as the black hole shrinks. Early on, it emits mostly harmless photons and neutrinos at a glacial pace, but as the black hole's mass decreases, its temperature rises exponentially. What started as a barely perceptible glow escalates into a roaring inferno of high-energy particles. A black hole with the mass of an asteroid would shine brighter than the sun, its surface temperature exceeding millions of degrees. In its final seconds, it would unleash a cataclysmic burst of gamma rays, a farewell fireworks display with the energy of 1,000 supernova compressed into a single blinding flash. Then nothing, proton decay, the hypothetical breakdown of matter itself, might be the only phenomenon outlasting them. Current theories suggest protons, the building blocks of atomic nuclei, could disintegrate after 10 to the 34 years. But even this timeline pales next to the endurance of the largest black holes. Sagittarius, a star, our galaxy's 4 million solar mass behemoth, would still be quietly simmering long after every proton in the cosmos has unraveled. Only then, in a universe reduced to a thin haze of leptons and radiation, would the last black holes finally wink out, their evaporating remnants leaving behind not even dust but a cold, featureless void. Yet the most haunting question isn't how they'll die, it's what they'll witness along the way. As the cosmos expands and cools, black holes will become the sole anchors of structure in an increasingly desolate landscape. Civilizations, if any persist, might cluster near them as cosmic oases, harnessing their energy to survive the encroaching dark. Some theories even suggest advanced beings could artificially prolong black holes' lifespans by feeding them carefully calibrated matter, stretching their evaporation timelines toward eternity. But entropy always wins. Eventually, even these last bastions of order will succumb, their gamma-ray death knells echoing through an emptiness where time itself has lost all meaning. This terminal phase reveals a profound irony. Black holes, often depicted as the universe's ultimate destroyers, will outlast everything else: stars, planets, even the fabric of matter itself. Their patient, inevitable decay serves as a cosmic hourglass, measuring out the last grains of meaningful time before reality fades to black. For all their ferocity, they'll exit not with a scream but a whisper, a final pulse of radiation so faint it would go unnoticed in today's vibrant universe, yet in that far future, it will be the last flicker of existence itself. From the inexplicable growth of billion solar mass black holes in the cosmic dawn to the eerie time-freezing paradoxes at their event horizons, these galactic titans continue to defy our understanding at every turn. Who could forget the monstrous Ton 618 laughing in the face of the Eddington limit, or the Phoenix Cluster's black hole that somehow became a stellar midwife against all odds? And what about those haunting gravitational hums, the universe's own soundtrack, composed by colliding supermassive black holes we've yet to directly see? The next decade promises revelations that could rewrite astrophysics. The Event Horizon Telescope, fresh from capturing that first iconic image of M87's shadow, is now turning its network of global antennas toward Sagittarius, a star's mysterious flares, and may soon catch a supermassive black hole in the act of a cosmic belch. Meanwhile, the LISA mission will extend our gravitational wave, hearing into frequencies 1,000,000 times lower than LIGO, tuning into the slow-motion mergers of black holes so massive their orbital periods span years. Together, these observatories could finally crack the final parsec problem or spot the elusive quantum hairs predicted to fringe every event horizon. But perhaps the greatest revelation isn't about black holes at all, it's about us. Every atom heavier than hydrogen, the iron in our blood, the calcium in our bones, was forged in stellar cores and scattered by supernova. Or perhaps even cooked in the accretion disks of quasars, as the camera pulls back from a brilliant quasar's heart, tracing its jet through the cosmic web to the 100 billion galaxies it connects. Carl Sagan's words echo with new depth. We are star-stuff pondering the stars' collected stellar ash grown conscious of its own origins. These mysteries aren't just out there in the void, they're woven into the fabric of our very being, reminding us that to study the cosmos is, in the end, to study ourselves.